Assalamu alaikum. Dear students and viewers, welcome to this series of programs on physics. Together we shall try to explore and understand the laws of physics with their applications. Our goal will be to introduce the basics and fundamentals. Today we shall discuss scalars and vectors. Can you tell what are scalars and vectors? Are they merely lines or symbols, or do they represent something from the world around us? And if this is the case, then why do we need to represent quantities through scalars and vectors? Mind it that science is all observation and experiment.
Hello, let's observe things around us. What is going on here? Everything is in motion. Now this motion can be translational, rotational, or vibrational. So let's explore the phenomenon of motion in detail. Although all types of motions are important in physics, presently we shall look into translational motion only. If we start moving from here, then we would travel some distance in a certain amount of time. We say that we have traveled 3 kilometers in 6 minutes. Since distance divided by time is speed, we could even say that we travel at a speed of 30 kilometers an hour. All these quantities can be expressed purely in terms of numbers. Such quantities are called scalars. But you can see that the information I have just given you is not enough to tell which point we reach after having traveled 3 kilometers. We could be going in the direction of the Faisal Mosque or in the opposite direction. We could even be going towards the right. So you can see that the specification of direction becomes very important on certain occasions. So if we were going towards the Faisal Mosque, we would say that we have traveled 3 miles northwards. So direction along with distance gives the displacement. Similarly, speed taken with direction is called velocity.
Well, I understand. Do you also? That in physics we come across quantities that can be divided into 2 types. Those without direction and those with direction. Scalars and vectors. Let's explore scalars further. A scalar is a physical quantity that is completely described by a number in proper units. For example, the number of people in a city can be expressed with just a number. It's the same as the number of pages in a book. Similarly, the measure of your waistline in centimeters, your weight in kilograms, 5 liters of milk are all scalar quantities that need no specification of direction. We can also look at the effect of change in light intensity. It might be written as 15 watts per meter square.
Now that we have understood quantities that exist without direction, let's move on to vectors. A vector is a physical quantity that requires the specification of both magnitude as well as direction for its complete specification. So a vector has 2 parts, magnitude and direction. Recall our example of going from 0 point to Faisal Mosque. When we say that we are going at 30 kilometers an hour, we have just described the speed, which is a scalar quantity. But it is also the magnitude part of the vector quantity, velocity. When we add that we are traveling northwards, then our vector quantity, velocity, is completely specified with magnitude in proper units, which is 30 kilometers per hour, as well as direction, which is northwards. Force given in newtons, push or pull, velocity, acceleration are all examples of vectors which require direction. In dealing with the direction part of a vector, let us now introduce the concept of a unit vector. The function of the unit vector is to specify the direction of a given vector. Mathematically, unit vector A is expressed as vector A divided by magnitude of A. Vector A has magnitude in proper units as well as direction, while magnitude of A is expressed in proper units. When vector A is divided by magnitude of A, we are left with the direction only. So we can say that unit vector A is a vector with magnitude 1 and no units.
now that we are familiar with the basic concepts of scalars, vectors, direction and magnitude, we can learn now how they are used in calculations and see what vector and scalar algebra is all about. As far as scalars are concerned, they are ordinary numbers. That means we can add, subtract, divide and multiply them like ordinary numbers. Consider this rectangle of dimensions 7 into 10 meters. Its perimeter is the sum of the lengths of its four sides. 7 plus 10 plus 7 plus 10 is equal to 34 meters. Since here we are considering just the length, which is a scalar quantity, the perimeter too is a scalar quantity.
On the other hand, a vector has both magnitude and direction. Vector addition, therefore, cannot obey the rules of ordinary algebra. A special algebra called vector algebra has been defined for the purpose. But before we move on to the details of addition and subtraction of vectors, let us clearly understand when and why it is that we need to add and subtract vectors. Take a look at this query. Common experience tells us that if we move with the current, we move quickly. That is, when the velocity vectors of the river current and the boat itself are in the same direction and add to each other. Similarly, if the boat moves against the river current, it slows down. Since here, the velocity of the water currents is in opposite direction and is subtracted from the velocity of the boat. The net effect is a slower velocity, replacing the original two velocities put together. You can see that the direction of the vectors being added or subtracted makes a very vital difference. Vectors are added by the head to tail rule. Let's see how. Consider three vectors A, B and C. The tail or end of the second vector is placed at the head or arrow of the first vector. Similarly, the tail of the third vector is placed at the head of the second vector. The resultant or sum of these vectors is obtained by joining the tail of the first vector to the head of the last and putting an arrowhead there. Let's join an experiment.
Dear students, while discussing scalars and vectors, we saw that vectors can be added by head to tail method. Now this can be very conveniently understood with the help of a law which we call as the parallelogram law of forces. Now to demonstrate that, we have got an apparatus over here, and this is called as the Gravesands apparatus. What we do is we just pass the thread over the pulleys, we suspend it over here on one end, similarly 40 gram on the other. Now these are the two forces acting in the opposite directions over here. So in order to form a parallelogram, we need a third force also. For this we have got another thread over here which we can pass through the thread. We bring it over here in the center. This is a mass of 50 grams. Now to get the positions of these three forces, we make use of this mirror and place it underneath the threads. Here you can see the thread and its image and the tip of the pen. All three should be in one line, and of course the eye. Similarly, we get another position, another point. Now 2 points representing each of the forces over here. Now you can safely remove these masses over here. You can write the masses over here. This was 40 grams. You can 40 G over here. Similarly 40 grams over here. And this one was 50. So 50 G over here. If you join these two, produce them to meet the first line at this point. because these were the three forces. These can be represented by, let's say, P. Similarly, we can call it Q, and let's say R vectors. So we put arrows. Now here you can see that P, R, Q, though these forces, they are acting over here in this direction, and R is balancing them. That's why it is acting in a downward direction right now. So in a way, if somehow we find the resultant of P and Q, that should be equal in length to R, which is acting in a downward direction. Because we are studying the parallelogram law of forces, so we need to make a parallelogram out of these two forces. If we can consider P and Q to be the two sides of the parallelogram, and then we make a full parallelogram. So right now I move OA, put a set square over here along the force P, scale over here, fix the scale over here, hold it tight and move the set square till it comes to the position, to the point B over here, a little bit over here. Now remove the ruler and then you can join the line. Mind it, we have not changed the angle. See, OA was pointing in this direction, we have just shifted it over here like this. Now when you have shifted OA over here, we can call it OA. This point A has been moved to this position, so we call it A dash. And you can forget about this now. And according to the head to tail method, you know that OB is a representative line of vector Q. This is the tail. I write small t over here just for vector Q. This was the head of the first vector, so you put a small h also. And again, OA vector which has been brought to its new position, I put, this is tail for the second vector and this is head. Okay. Head of the second vector, tail of the second, head of the first, tail of the first vector. That's why it is called as the head to tail method. Now according to the same method, if you join this tail of the first with the head of the last, you will get a certain line. So you can draw it with the red pen also. Just to indicate that it is the resultant of. Now it's resultant, so I put R over here. Again it's a vector, so I put arrow over here. Now you've got a complete parallelogram O, A dash and B. This is the reason it is called as the parallelogram law of forces, or for vectors, for addition of vectors.
We can find many interesting examples of vector addition around us. See for instance how the weight of this bucket is balanced by the force exerted by the two children. Note that the weight W of the bucket acts downwards, but we can see that child A exerts force FA and child B force FB in different directions. It is then the resultant F of these two forces which acts in the upward direction and balances the weight of the bucket. For further clarity on vector subtraction, let's take a look at this tug-of-war game. The two teams apply force in opposite direction. When these two forces are equal, the rope does not move, since the vectors subtract from each other and cancel their net effect. However, when one of the forces is greater, the rope starts moving in that direction. This motion corresponds to the difference obtained after subtracting the smaller force from the larger one. We have seen how two or more forces can be added together and replaced by one force. Sometimes we have to do the reverse and split or resolve one force into two forces, called its components. Just as I can take this piece of chalk and break it into two parts. Then although disjointed, this remains the same chalk. All we have to do is to put this chalk back together.
When the components of a vector are perpendicular to each other, they are known as rectangular components. Let's see how vector A, which we have represented by OP, can be resolved into two components, OX and OY. If a perpendicular is drawn from P to the OX axis at the point Q, then the sides OQ and QP of the triangle OQP give the required rectangular components AX and AY of the vector A on the same scale as OP. Applying the laws of trigonometry on the triangle OPQ, we get AX is equal to A cos theta and AY is equal to A sin theta, which gives the magnitudes of the two components. Since AX is along the x-axis, its direction is given by I. The direction of AY is given by unit vector j. So that in vector form, vector AX is equal to A cos theta into unit vector I, and vector AY is equal to A sin theta into unit vector j. We can take the familiar example of a garden roller. If it is being pulled by a total force of 20 newtons acting at an angle of 50 degrees with the ground level, then the component of the force which makes it move along the ground will be Fx is equal to F cos theta, which is equal to 20 cos of 50 degrees, which is equal to 20 into 0.6428, which gives 12.9 newtons.
When two quantities are being added or subtracted, they must have the same units so that the result has the same unit as well. But in the case of multiplication, the quantities being multiplied do not necessarily have the same units. So this means that we can define three kinds of multiplication operations involving vectors. First, multiplication of a scalar with a vector. The scalar may have units different from vectors. This simply gives a new vector having the same direction but different magnitude and possibly different units. Let's go to our earlier example. If the velocity 30 kilometers per hour northwards is multiplied by 1/10 of an hour, we would get 3 kilometers northwards, which is the displacement. We would make in 1/10 of an hour or 6 minutes. Mathematically, we can write vector v multiplied by time is equal to 30 kilometers per hour northward into 1/10 of an hour, which is equal to 3 kilometers northwards.
One of the possibilities is that we multiply two vectors and the product is a scalar quantity. Now, as you proceed in your studies of physics, you will see how quantities like work, electrical potential, and many others can be expressed in terms of scalar products. Now, we could have defined the scalar product in many ways, but the only way that gives physically meaningful results is A dot B equals magnitude of A into magnitude of B into cos theta. Here, theta is the angle between vector A and vector B. Since magnitude of A and magnitude of B are both scalars and cos theta is a number, therefore A dot B has to be a scalar. If we drop a perpendicular from B on A, then here OP is equal to B cos theta, which is the projection of B along A. Therefore, the scalar product can be regarded as the product of the magnitude of A and the projection of B along A. It is also possible to multiply two vectors A and B and obtain a third vector C. We define the magnitude part of C as the magnitude of A multiplied by the magnitude of B multiplied by sine theta. Theta is the smaller, not the greater angle between A and B. It is important to take this into account since sine 2 pi minus theta is equal to minus sine theta, and that would change the sign of the result. Now, what about the direction of vector C? If we consider vector A and vector B, then whichever direction they point in, together they will always lie in a plane. The direction of their cross product, the vector C, will be perpendicular to this plane. Now you can see that there are two such directions, one above and the other below the plane. Which of these directions is the direction of the vector C is determined by the right hand rule. If I curl the fingers of my right hand from vector A towards vector B, then the direction of my thumb gives the direction of the vector C. From here, you can see that A cross B is not equal to B cross A. They are equal in magnitude, but they are opposite in direction. For the Cartesian coordinate system, this is your x-axis, your y-axis and your z-axis. Now you can see using the right hand rule that I cross j points along k, while j cross I points along the negative z-axis, that is the minus k direction. Also, j cross k points along plus I, while k cross j points along minus I. Also, k cross I points along j and I cross k points along minus j.
So, in today's program, we have been able to introduce ourselves to the basic ideas relevant to vectors. First, in physical quantities, two aspects are very important, those of magnitude and direction, and that the direction is specified by a unit vector. Number two, we need special rules for vector addition, and that a vector could be resolved into its components. And finally, we learned that there are three kinds of multiplications involving vectors. Number one, the product of a scalar and a vector which gives another different vector in same direction. Number two, the product of two vectors which gives a scalar. We can also call it dot product, like A dot B is equal to AB cos theta. Number three, the product of two vectors which results in another vector in different direction. See you in the next program. Allah Hafiz.